Assalamu alaikum dear students. I hope you are fine by the grace of Almighty Allah. I welcome you all to the 13th lecture of Thermodynamics 2. Lecture 13. The contents of lecture 13 are Carnot second principle and the proof of Carnot second principle. Effect of temperature on the performance of reversible devices. These devices include heat engines and refrigeration and heat pumps. And we will also find the more effective way of increasing the efficiency of Carnot cycle, numerical problem and conceptual questions and answers. Carnot principle and the statement of Carnot second principle is efficiency of all reversible heat engines operating between the two same energy reservoir is same regardless of working substance employed or operation details. So you can see the schematic diagram of two reversible Carnot heat engines. At the top you can see the source, that is the high temperature thermal energy reservoir, and in the middle you can see two reversible heat engine, reversible heat engine 1 and reversible heat engine 2, and at the bottom you can see the sink. Sink is the low temperature thermal energy reservoir. So for reversible heat engine 1, it is receiving QH1 amount of thermal energy from source and rejecting QL1 amount of thermal energy into the sink, whereas the output is W reversible 1. For reversible heat engine 2, it is receiving heat from the source QH2 and rejecting QL2 amount of heat into the sink, and it is producing W reversible 2 amount of work. So the statement suggests that if we have two reversible heat engines, then the efficiency of both heat engine will be same. Mathematically it can be expressed eta heat engine 1 is equal to eta heat engine 2. The efficiency of heat engine 1 is equal to the efficiency of heat engine 2. The formula for efficiency is eta, that is the function of TH, that is temperature of high temperature thermal energy reservoir and temperature of low temperature thermal energy reservoir. TH is the temperature of source and TL is the temperature of sink. Now we have the proof of Carnot second principle. So before going into the proof, I want to just remember in the previous lecture, as you can remember, that we have proved that the efficiency of reversible heat engine is always greater than the efficiency of a reversible heat engine. That is the Carnot first principle. So now we will prove that the efficiency of two reversible heat engines that are connected to the same low and high temperature thermal energy reservoirs, that means if we have two reversible heat engines that have same source and same sink, then the efficiency will also be the same. So statement of Carnot second principle: efficiency of all reversible heat engines operating between the two same reservoirs is same. To prove this, we have to prove eta A is greater than eta B and eta B is greater than eta A wrong. So if we can prove both this condition wrong, that means eta A will be equal to eta B. Okay, eta A is the efficiency of heat engine A and eta B is the efficiency of heat engine B. So if we want to prove that they have both have same efficiency, then we have to prove that wrong, that one of them has greater efficiency. So in mathematics, that is the deduction method, and here we will assume in the case 1 that eta A is greater than eta B, that the efficiency of heat engine 1 is greater than the efficiency of heat engine B. So the efficiency of heat engine A is WA divided by QH, and efficiency of heat engine B is WB divided by QH. Since they both have same amount of QH, therefore WA is greater than WB. As both engines are reversible, therefore the direction of heat engine can be reversed. So as you can see, we have reversed the direction of heat engine B. So heat engine direction is reversed. Since WA is greater than WB, therefore the work output of heat engine A will give input to the heat engine B. Now as we have reversed the direction of heat engine B, now it is not a heat engine, it will work as a refrigerator. Therefore a work input will be needed to run this refrigeration system, because it is taking heat from sink and rejecting it into high temperature thermal energy reservoir, so it will require WB amount of work. So as we have proved that the work output of heat engine A is greater than work output of heat engine B, so we will connect this work output WA into as the input of heat engine B. Now you can see the heat engine A output, work output A WA is the input of heat engine B that is now acting as a refrigerator. So WA is the input and W net is the WA difference between work WA minus WB. Now QH amount is the amount of heat rejected by heat engine B, whereas the same amount of heat is input of heat engine A. So you can see with the red arrow, QH is the amount of heat that is rejected by reversible heat engine B, and it is QH that is the same amount of heat that is received by heat engine A from source. Therefore, we have removed the source and directly connected both lines. So now the QH amount of heat that is rejected by heat engine B becomes the input of heat engine A, QH amount of heat that is received by heat engine A. Since the current process does not require second thermal energy reservoir, this violates the Kelvin-Planck statement of second law of thermodynamics, because Kelvin-Planck statement of second law of thermodynamics states that you cannot produce a work through a single thermal energy reservoir. You should require at least two thermal energy reservoirs to produce a work through heat engine. Therefore, our initial assumption that efficiency of heat engine A is greater than efficiency of heat engine B is proved wrong. Now, for case 2, we will assume that efficiency of heat engine B is greater than efficiency of heat engine A. For case 2, the procedure is same as the case 1, but we have to reverse the direction of heat engine A in this case, and then we can prove that efficiency of heat engine B is not greater than the efficiency of heat engine A. Therefore, the only possibility left is the efficiency of heat engine B is equal to the efficiency of heat engine A. So both reversible heat engines will have the same amount of efficiency. Now on the right hand side, you can see that the efficiency of a reversible heat engine is a function of the temperature of high temperature thermal energy reservoir and the temperature of low thermal energy reservoir. Therefore, TH is the temperature of source and TL is the temperature of sink. The formula for the efficiency of heat engine is eta reversible is equal to 1 minus QL divided by QH. QL is the amount of heat rejected into the sink and QH is the amount of heat received from source. So as the efficiency is the function of TH and TL, so the efficiency in term of TH and TL is given by eta or efficiency of reversible heat engine is equal to 1 minus TL divided by TH. Therefore, for reversible heat engines, QL divided by QH is equal to TL divided by TH. Effect of temperature on the performance of reversible devices. For heat engines, thermal efficiency of Carnot heat engine is given by eta Carnot or thermal energy efficiency of Carnot heat engine is 1 minus TL divided by TH. Therefore, the efficiency of Carnot heat engine can be increased by option 1 decreasing TL because TL is in the numerator and increasing TH and TH is in the denominator. So now we have to find what is the more effective way of increasing efficiency of Carnot heat engine, because we have two methods, decreasing TL and TH. So we will find what is more effective. Is decreasing TL is more effective or increasing TH is more effective. So here we have a mathematical proof and we will find the more effective way of increasing efficiency of Carnot heat engine. For heat engines, efficiency of Carnot heat engine is given by 1 minus TL divided by TH. Efficiency can be increased by decreasing TL and increasing TH. So for case 1, we will decrease the lower temperature by delta T. So TL is the temperature of low temperature thermal energy reservoir TL. So we will further decrease it by the amount delta T. For example, if the temperature of low temperature thermal energy reservoir is 20, we will further decrease it by an amount delta T. For example, delta T is equal to 3. So TL is 20 degrees centigrade and we will further reduce it by 3 degrees centigrade. So now you will have a comparison what I mean, TL minus delta T. And for case 2, we will increase high temperature by TH. So TH is the amount of TH is the temperature of high temperature thermal energy reservoir. So we will further increase TH by an amount delta T. So eta 2 is equal to 1 minus TL divided by TH plus delta T. So we have in eta 1 thermal efficiency 1, we have decreased the low temperature, and in efficiency 2 we have increased the higher temperature. Now we will subtract equation 2 from equation 1. On the previous slide we have individual expression for eta 1 and eta 2. Now we will find the difference. So eta 1 was 1 minus TL minus TH divided by TH minus 1 plus TL divided by TH plus delta T. Eta 1 minus eta 2 is equal to TL divided by TH plus delta T minus TL minus delta T divided by TH. That is a little mathematics involved in this proof because it's a mathematical proof. So we just have cancelled out 1 from 1 minus 1. We will cancel out, and the last term we have put it in the first. So TL term here and TL minus delta T is on the right hand side. So here we are taking the LCM. So eta 1 minus eta 2 is TH TL minus delta T into TH plus delta T whole divided by TH plus delta T into TH. So we have here multiplied both these brackets. So eta 1 minus eta 2 is TH TL minus TH TL minus TL delta T plus TH delta T plus delta T square whole divided by TH into TH plus delta T. So eta 1 minus eta 2 is equal to TH delta T minus TL delta T plus delta T square whole divided by TH into TH plus delta T. In the numerator we have taken delta T common, and in the bracket we have left with TH minus TL plus delta T square whole divided by TH into TH plus delta T. Now as the TH, that is the temperature of high temperature thermal energy reservoir, is greater than TL, that is the temperature of low temperature thermal energy reservoir, therefore the term eta 1 minus eta 2 is a positive value. So because the only minus sign is in the numerator and their solution is also a positive value, therefore the expression eta 1 minus eta 2 has the positive value. Therefore decreasing low temperature TL of Carnot heat engine is more effective way of increasing efficiency of Carnot heat engine. because eta 1 was the, in eta 1 we have reduced the TL by delta T, and eta 2 we have increased TH by delta T. So if the value of eta 1 minus eta 2 is positive, the then decreasing low temperature TL is the effective way, and if its sum was negative, then increasing TH was the effective way. But in our proof we have calculated that eta 1 minus eta 2 is a positive value, therefore decreasing lower temperature TL of Carnot heat engine is more effective way of increasing efficiency of Carnot heat engine. Now for refrigerator and heat pumps. So as we know that the efficiency of refrigerator and heat pump is given by the coefficient of performance, and coefficient of performance of refrigerator is equal to TL divided by TH minus TL, and coefficient of performance of heat pump is equal to TH divided by TH minus TL. So on the right hand side you can see in the middle we have a refrigerator system, and refrigerator is receiving QL amount of heat from refrigerated space, that is the cabinet of fridge, and rejecting QH amount of heat in the atmosphere. For example, if we have put the refrigerator into the kitchen, then kitchen atmosphere will be its ambient or high temperature thermal energy reservoir, and refrigerator is a work consuming device, therefore we have to provide W amount of work to the refrigerator. So if we want to increase the COP of refrigerator, then we have the same two cases. So now we have case 1, that if we want to increase the coefficient of performance of refrigerator, then we first case is by increasing the value of TL. TL is the temperature of refrigerated space, and the case 2 is by decreasing the value of TH. TH is the temperature of atmosphere, ambient or kitchen atmosphere, or wherever the external atmosphere or surrounding where fridge is placed. So in the right hand side in the box you can see the proof is same, the mathematical proof is same as we have proved in the previous slide. So the results deduced are to increase the coefficient of performance of heat pump or refrigerator, increasing the low temperature thermal energy reservoir is more effective rather than decreasing the higher temperature thermal energy reservoir. So here is a question: why COP of refrigerator is higher in winter? So after that mathematical proof, you can now answer the question, as you have seen the answer that increasing the low temperature is more effective rather than decreasing the high temperature. So the coefficient of performance of refrigerator is higher in winter. The reason is during winter the ambient temperature is lesser than summer. So you can compare it that if you have a fridge that is placed in your university, so in the summer the ambient temperature reaches up to 40 degrees centigrade approximately, and in winter the ambient temperature in which the refrigerator is placed can be decreased up to 15 degrees centigrade or maybe lower. So the ambient temperature is lesser than summer. Since denominator is lesser, so Th minus Tl, the difference is reduced. Therefore, coefficient of performance is increased. So in winter, lesser work is required in the refrigerator. So as the value of Th minus Tl is reduced, so lesser work is required in the refrigerator. Conceptual questions. So the first conceptual question is, if the efficiency of power plant goes up as the low temperature drops, why do power plant not just reject energy at say minus 40 degrees centigrade? So in the current lecture, we have proved that if power plant, you can compare power plant as a heat engine as well, because it is receiving heat from high temperature, that is source, and rejecting it in the atmosphere, that is sink, and while producing the work. So we have proved that rejecting the one of the way of increasing the efficiency of heat engine or power plant is to rejecting energy in a low temperature thermal energy reservoir, that is we can further reduce that TL minus delta T. So here the question asked is, if the efficiency of power plant goes up or increased as low temperature drops, so why do power plant not just reject energy that is very low or say minus 40 degrees centigrade? In order to reject heat, in this case the ambient or atmospheric temperature must be very low. It would be only possible if we move the power plant to the region where atmospheric or the external temperature is very low, that is minus 40 degrees centigrade, like north poles. So as we have no way of rejecting energy in the very low temperature like minus 40 degrees centigrade, therefore we cannot use that idea. So we cannot create and maintain our own thermal energy reservoir. So we have to work wherever the power plant is based. So the atmosphere surrounding the power plant will be the low temperature thermal energy reservoir with respect to that power plant. If the efficiency of power plant goes up as the low temperature drops, why not let the heat rejection goes to a refrigerator at say minus 10 degrees centigrade instead of ambient 20 degrees centigrade? So the second conceptual question is somewhat linked to the first conceptual question. So in the first conceptual question, the question asked was, as the efficiency of power plant increased as we decrease the low temperature thermal energy reservoir. So in the first conceptual question it was asked, then why can we not reject it into minus 40 degrees centigrade? So that answer was that the uh, power plant, if it is placed in the north pole or the region where the external temperature is very low, then we can utilize that. But however, in the real world, power plants are based on different geographical positions. So the surrounding will work as the ambient or low temperature thermal energy reservoir. And in the second conceptual question, it is asked if we have a power plant, if there is, that is the limitation, that why cannot we reject the heat into the refrigerator. So the answer is, so if we want to reject the heat into the refrigerator, like the to decrease the thermal energy reservoir sink, so the refrigerator must pump the heat up to 20 degrees centigrade to reject it into the ambient. The refrigerator must then have a work input that will exactly offset the increased work output of the power plant. If they are both ideal, as we cannot build an ideal device, the actual refrigerator will require more work than the power plant will produce in excess. So if we you can see that if we want to reject the heat into a low temperature thermal energy reservoir, and if we want to further reduce the temperature of low temperature thermal energy reservoir or sink, and we are rejecting the heat of power plant into the refrigerator, so refrigerator is a work consuming device. So it is said that the amount of energy that we will produce in excess through power plant by rejecting heat into the refrigerator will be lesser than the amount of energy we have to provide to the refrigerator. Conceptual question 3. A coal-fired power plant operates with high temperature of 600 degrees centigrade, whereas a jet engine has 1400 Kelvin. Does that mean we should replace all power plants with jet engines? The thermal efficiency is limited by Carnot heat engine efficiency. It means that the low temperature sink temperature is also important. In power plant, heat is rejected in much lower temperature than the jet engine has in the exhaust flow. Therefore, it is not necessarily that the jet engine has a higher efficiency than power plant. So as you know that the Carnot efficiency is given by will depend is a function of TH and TL. So it is not possible to directly suggest that the efficiency of jet engine will be higher than the power plant, because the sink temperature of jet engine is much higher than the sink temperature of power plant, and efficiency depend on the sink temperature as well. Numerical problem. The statement of numerical problem is: a large stationary diesel engine produces 15 megawatt of energy with thermal efficiency of 40%. The exhaust gas, which we assume is air, flows out at 800 Kelvin and the intake air is 290 Kelvin. Calculate the mass flow rate, assuming this is the only way of heat rejection. So as the efficiency of heat engine is W dot over Q H dot, so to calculate the rate of heat energy received by diesel engine is Q dot H is equal to W dot divided by eta thermal. So W dot is 15 megawatt and efficiency is 40%, 0.4. So Q dot H is 37.5 megawatt. That means 37.5 megawatt of energy is reduced by diesel engine and 15 megawatt work is produced. So according to energy equation, Q dot L is equal to Q dot H minus W dot out. So 37.5 minus 15 is 22.5 megawatt. So that is the energy rejected into the atmosphere. So as we have the temperature, so from steam table we will find the value of enthalpy. So exhaust flow is Q dot L is equal to m dot into H 800 minus H 290. So for enthalpy value of at the temperature of 800 and enthalpy value at the temperature of 290, so this value will be find out through the steam table. So mass flow rate is Q dot L divided by H 800 minus H 290. So as 22.5 unit is in megawatt and 822 unit is in kilojoule per second. So we will first divide that to convert that into megawatt, and the unit conversion will be for m dot is 42.3 kg per second. So second numerical problem, the statement of second numerical problem is a combination of two refrigerator cycle is shown in figure. So the it's a problem 7.7, and on the right hand side you can see the figure. So the first we will understand the figure. So here we have two refrigeration system in series. So you must remember the function of refrigeration is to take out heat from sink and reject it into the source. While it will require a work done. So for refrigeration 1, it is taking QL amount of heat from sink, that is at temperature of TL, and the work required is W1, and is taking out into that Tm is the middle or intermediate, you can see. So the output of refrigeration 1 is the input of refrigeration 2. So refrigeration 2 or refrigerator 2 is taking Tm amount or Q dot M amount of heat from low temperature. So the high temperature or source of RF1 refrigerator 1 will become the sink of refrigerator 2. So because they are connected in series, and W2 is the amount of work done on refrigerator 2, and refrigerator 2 will reject Q dot H amount of heat into high temperature thermal energy reservoir. So both of these refrigerators are connected in the series. So in the numerical, you are asked to find the overall coefficient of performance as a function of COP1 and COP2. So the coefficient of performance is QL divided by W total. So QL is the amount of heat that is taken out from T sink. So that is the fridge cabinet, and that is a refrigeration system somewhere that is in series. So QL amount of heat is taken out, and the work required is W1 plus W2, that is the total work done WT. So QL Here we have multiply and divide by W1. So QL divided by W1 into W1 divided by WT. So WL divided by W1, WL divided by QL divided by W1 is the coefficient of performance of refrigerator 1, and on the right hand side we have left with W1 divided by WT. So here we know that WT is W1 plus W2. So here first we have written W1 plus W2, and W1 that is in the numerator we have divided that at the bottom. So it will left 1 plus W2 over W1. So here it is also written, where we have used W total is equal to W1 plus W2. So here W total will be replaced by W1 plus W2, W1 plus W2, and that W1 is divided in the denominator. Now we use the definition of coefficient of performance 2 and the energy equation of refrigerator 1 to eliminate Q dot M. So as that Q dot M and Tm is the intermediate heat transfer and temperature, so we want to remove that function. So the coefficient of performance, if we want to know the coefficient of performance of refrigerator 2, then it the Qm is the amount of heat that refrigerator 2 is taking out, and QH is the amount of heat rejecting into ambient. So W2 is equal to Q dot M divided by COP2. So W2 is equal to, here we have W dot 1 plus QL divided by COP2. So Q dot M is replaced by W1 and QL. So here we have used the energy equation, because Qm is out and 2W1 plus QL is incoming into the refrigerator. So if we divide W1 on both hand side, then the left side becomes W2 over W1 is equal to W1 divided by W1 is 1, and QL divided by W1 whole divided by COP2. So QL over W1 is the COP1. So W2 over W1 will become 1 plus COP1 divided by COP2. Finally substitute into the first equation and rearrange a little. So W2 over W1 value, that is 1 plus COP1 divided by COP2, we will put that value here and rearrange this. Then the overall coefficient of performance in term of COP1 and COP2 is given by COP1 into COP2 whole divided by COP1 plus COP2 plus 1. So that was asked in the numerical to find the relation in overall coefficient of performance in term of individual coefficient performance of refrigerator 1 and refrigerator 2. So numerical problem, the statement is, let us consider that heat engine that receive heat transfer rate of 1 megawatt at high temperature of 550 degrees centigrade and reject energy to the ambient surrounding at 300 Kelvin. Work is produced at a rate of 450 kilowatt. Calculate how much energy is discarded to ambient surrounding and the engine efficiency, and compare both of these to Carnot heat engine operating between the same two reservoirs. So heat transfer rate is 1 megawatt at high temperature. So Q dot H is 1 megawatt, and the temperature of source is 550 degrees centigrade. So we will convert that degree centigrade into Kelvin. The temperature of ambient, that is TL, is 300 Kelvin. Work produced at a rate of 450. So W dot is 450 kilowatt. So we have to find the energy that is rejected into the ambient surrounding and the engine efficiency, and we will have to compare that efficiency with the Carnot engine. So Q dot L is equal to QL is equal to QH minus W. So 1000 is QH minus 450 is the work. So QL is the 550 kilowatt. That is the rate of heat rejection into the sink. So the thermal efficiency is given by W by QH, and W is 450, QH is 1000. So the efficiency of heat engine is 45%. Now comparing that efficiency with the Carnot heat engine. So efficiency of Carnot heat engine is given by 1 minus TL divided by TH. So TL is 300 and TH is 550 degrees centigrade. Here we have converted this into the Kelvin, and the efficiency for the same temperature thermal energy reservoir, high and low temperature remains same. The efficiency of Carnot heat engine will be 63.5%. So the rate of work and heat rejection becomes, so work is eta Carnot into QH. So for 63.5% efficiency, the work output will be 63.635 kilowatt, and the rate at which heat will be rejected into sink is 365 kilowatts. The refrigerator, the next numerical is, the statement is, the refrigerator in a kitchen receive electrical input power of 150 watt to drive a system, and it reject 400 watt to the kitchen air. Find the rate of energy taken out of the cold space and the COP of the refrigerator. So the coefficient performance formula is COPR is QL divided by QH minus QL, and here you can see the schematic diagram is also shown that 150 watt of work is done on the refrigerator, and it is rejecting 400 watt of energy into the high temperature thermal energy reservoir. So Q dot L is the difference of QH and W. So QL is 250 watt, and the coefficient of performance of refrigerator is QL divided by W, 250 divided by 150, that is 1.67. So the coefficient of performance of refrigerator in the kitchen is 1.67. So home assignment for lecture 13 are, all students are advised to go through example problem of each topic discussed in this lecture. All students must submit handwritten lecture summary report minimum 3 pages before the commencement of next lecture. So all students are advised to submit hard copies of every assignment and report. So in the current scenario, you can write a lecture summary report and scan it and mail it to my email ID, that is arslan@viitva.edu.pk. So all students are advised to prepare previous lecture thoroughly before the commencement of next class, as there will be a viva and oral question answer session for every student. Take care. Thank you very much. Allah Hafiz.